y'all decided where you guys are gonna teach next month?
Mm-hmm.
Ready for start teaching 4,000?
And teach for 1,000. Observational astro. And then maybe math methods 1. Word.
Who's teaching quant?
Karen, probably.
I'm office.
Yeah, you don't want to do quant?
I do want to teach quantum, but she has she's done it a lot. She's almost retired.
What's a class that you want to teach but you haven't taught yet?
Feedback here. Will, can you mute yours?
Am I not muted?
Well, hold on. Let's do. Well, you'll need to speak, right? So let me do this. Try that now. Are you speaking? Yeah.
Will's my guy.
Okay.
Guy?
Yeah. So Will and the screen are having the same feelings. Will was supposed to come in for an early morning check-in, and I missed the appointment because I put it in on the wrong date. So he was there, ready to go, and I wasn't. And so instead, I had him do his check-in during lunch when he was supposed to be prepping for today's class. So he expressed that if it's not ideal, scream at me. But don't scream at me either, because that's not nice. I don't know what to do about that. That's gonna cause me to have an aneurysm. Did you do that? Oh, why did you do that? Oh, okay. Okay. All right. So if you are on Slack, or sorry, if you're on Zoom, I think that'll be better. Because right now what's happening is Will is projecting the book. So we can just do that.
We just join
on Zoom, yeah. Because I don't know what to do about this, so I'm gonna unplug it before we lose our mind. Is that okay? All right, Will, whenever you're ready. Everyone on Zoom? Raise your hand if you're not on Zoom. Okay. Who has not had their check-in for this class? Who has not planned their check-in? Good. All right, good. Do you need to do a check-in to pass the class? Yes, that's correct. If you miss all your check-ins, can you pass the class? No, that's correct. Are they stressful for people who've already done them?
No.
No.
So relieving.
So relieving. Go ahead.
How many seconds do we have in this?
3. We'll have another one in like 5 weeks, and then we'll have the final. Okay, we're on Zoom because the screen is having a connection fit. All right, Will, whenever you're ready.
So when this chapter talks about varying step size, it's talking about varying the step size h that we've been using in the Runge-Kutta method. So instead of having a constant h b minus a over n, you would vary that h depending on some parameters that we're going to address in the chapter, in the section of the chapter. And it's called the italics. It says adaptive step size method. So it's called the adaptive step size method, keyword. The purpose of the adaptive step size method is to vary the step size h so that the error rendered per unit interval, in this case t, it's usually t as we've been using, or it could be, yeah, t. Per unit interval in the independent variable t is about constant or roughly constant. This method is used, instead of the Runge-Kutta method because the accuracy of the Runge-Kutta method is retained in this method, and then it also increases the efficiency and the speed of the calculation because fewer points are needed in the adaptive step size method. And then it says the program we are going to generate is designed to choose the best H value at each step, which means we're going to solve for H at every iteration in the for loop. Is it a for loop? Yeah, it's a for loop for the Runge-Kutta method, and for each new iteration of H, we're going to calculate a better and different H, and it'll be either bigger or smaller than the original H that we chose.
So for folks who just arrived, we're on Zoom because the screen is freaking out. Okay. Okay, Will, how do we do this?
There's a graph that shows it. It's I can get to it later. I kind of want to get to it, or do you want me to skip? You want to skip the error part?
You can sort of gloss over it, but the calculating the error is not the important part.
So the constant error per unit time is, for example, this 0.001, and we want to retain that throughout the entire rendered code. For like, so here the step size is larger when the slope is small, but then when it increases, it gets larger, really large, then the step size gets really, really small to render those small changes and to get a more accurate picture, but keeping the error per unit time constant. And so to do this, there's two parts, really three parts, but it doesn't include the third part, because it has two parts. First, estimate the error of the steps. And then increase or decrease its step size to achieve the accuracy that we want based on the estimated error that we wanted to achieve. And then the third step is either, depending on whether you increase or decrease the step size, you repeat the calculation of H that you just did, and get a new point for your X value. Let's say X is, even though it's, let's say it's X over T graph, not Y over T or Y over X. So X is the dependent variable and T is the independent variable. Then you either repeat the calculation for X using this estimation method, this new Runge-Kutta method, but different Runge-Kutta method, or you move on to the next point, and whether you increase or decrease. So what you do is you estimate two steps, a double step for X of T of plus 2H, and you do it twice. So you have an X1 and an X2. X1 shown in the graph is iterating over two steps, H and H, and then you calculate the estimate Runge-Kutta method X2 using a large 2H and in that same, they're going to be roughly equal, but there's going to be a difference between them, and we use that difference as using the system of equations. So we have the system of equations, and when you solve it for epsilon or CH to the fifth, which is the first step error, you get 1 over 30. This is important. 1 over 30 X1 minus X2, because it comes from this error, and this error in x2. That's why you get the 1/30. So you get this, and now you want to calculate the new h that you want to. So you have your h that you originally chose, but then you want to calculate h prime, it calls it, which is the new h you want to iterate with, and you solve it using this equation. And the important part is rho. Rho is the ratio of the target accuracy to the actual accuracy. And so when you calculate, because you have two Runge-Kutta methods you're calculating. You have x1 you're calculating and x2 you're calculating for each iteration step. And if the x1 over x1 minus x2 over 30 is less than your target accuracy, which you've calculated, and then that's the step for it, right? If it's smaller than your target accuracy, then rho is greater than 1. And that means your Runge-Kutta method, your Runge-Kutta step is sufficiently small, and your target accuracy, your actual accuracy is sufficiently small. So that means it does mean that there's a waste, because if your h is too small, then if rho is greater than 1, that doesn't mean that it means that your actual accuracy is more accurate and smaller than it needs to be. Then there's a waste there. And so what you do is you just move on to the next step, and you just continue in the for loop to the next point you want to calculate. And let me just and you increase the step size, because now you can be less accurate. So you'll have a wider h that we saw on that graph before. You'll have wider h like this instead of the thinner h like this. If rho is less than 1, then your actual accuracy is greater and therefore poorer than the target accuracy. And so you need to repeat this. You don't get to move on to the next point calculation. You have to repeat this point calculation and find a new x1 in this case, because you don't use x2. You use x2 to calculate the error, but you use x1 as your final solution, and which we'll talk about later. And so in this case, you need to repeat. If its rho is less than 1, you have to repeat the calculation and decrease h so that it's more accurate, because your accuracy wasn't enough, so it has to be more accurate. And so depending on what rho is, you either increase and move on, or you decrease and repeat the step.
That makes sense? Everyone following along? Okay, I think it makes sense to sort of pause here unless you have anything else to say, because this is where we should work as a group to actually show what this looks like.
Oh, sometimes x1 and x2 can be equal. In that case, this denominator goes to 0, and the rho goes to infinity, which means your new h prime will go to infinity. But to avoid that, you want to make sure that h does not increase, or maybe decrease as well, we would just increase, does not increase by more than a factor of 2 for any given pair of steps. Does that, let's do, oops, maybe I'll just skip that. That makes sense, okay. I didn't fully understand the simultaneous differential equations section. It was simple, but also like really phrased,
What do you mean by that? So scroll down a little bit more.
or just this part.
Oh, those aren't differentials, right? That's solving the, if you have multiple time steps in order to solve, or sorry, multiple spatial steps, right? That they're both in multiple dimensions, you can be changing the step. We'll get to it. Yeah. Let's try to do one dimension at a time because this will be complicated. I promise you. You will hate it. Anyone hate it already? Good.
That's it.
Let the record show no one hated it. Okay. Questions? Okay. So how are we going to do this? In practice, I'm going to take the screen back if that's okay. Yeah, I'll try and write on the board here so people can see this. Okay. What's the goal? Yeah. We have a goal that we want to keep it under some accuracy. Okay. So you're going to have some target accuracy. What did we call it in the book?
PH to the 5th.
No, that's the true accuracy. What's our target accuracy? It's in row. Nope, 30 comes along for free. Make our lives better.
Does it have row in it?
No, it's inside of row. Out of the definition of row.
H delta?
Delta. Delta is our target accuracy. Okay. Okay. So the goal here is to go between points A and B. And we're going to compare x1, which is taken with one step of H, to, I might have done this wrong. The x2, which is taken with 2 steps of H. Right? And then we want to see how far apart these are from one another. And this will lead us to 2 outcomes. What are the 2 outcomes? Anyone? Okay. What happens if 30 delta H is bigger than x1 minus x2? What does that mean?
parentheses would know.
You did a good job. H, good. Right? So you say, congrats. And then what do you do?
Move on to the next step.
What happens after the next step, or what happens during the next step?
Increase H.
Increase H, move to next step. Okay, and what if that's not true? What if 30 delta H is less than their difference? Boo, right? Tomato, tomato. Good. So boo. What do you do now?
Decreasing.
You decrease H. Redo. You see the flow chart? Pretty flow. Okay. This is how you should draw it out on paper. Right? You can actually see the steps in order. Right? This isn't code yet. We haven't gotten there. Okay, so we have some target, we take some step, we change it. We understand all that. We feel like experts now, right? No. So now let's turn it into just some framework for code. So how am I going to go through this process? How am I going to understand how to make this picture that I drew on the board into code? Okay, so I like that instinct, but I'm going to push back against it. The user-defined function is not for Rangakata, but for the function itself, right? Whatever it is that's giving us the derivatives. The H is something that we feed Rangakata. So this will happen before the Rangakata step, right? And it will sandwich it, we'll envelop it. Because we'll take 2 Rangakata steps here, and we'll compare them to 1 Rangakata step that's twice as large. Okay, so let's take a step out from that. You have been doing Rangakata with what type of loop? For loop. Is that the only type of loop? No. Is a for loop appropriate here? Why, yes.
Because you could say if 30 delta H is greater than x1 minus x2, proceed. If not, stop.
So that sounds like an if statement, not a for loop. So you're right. There is a bifurcation, right? Anytime I see this, that tells me that I need an if statement. Good. What type of loop do I need in order to do all of the points? Yeah, but for something in the range, doesn't that normally tell me to go from point A to point B with a specific number or sized step? Yeah. So that's going to fail us here. And we have to go back into our memory holes and find a different type of loop.
Wow.
A while loop. Okay. So we need a while loop. Now, what's the condition for the while loop? When do we want it to stop? Yeah, that's exactly it. When you get to the end. When you get to the end. Don't write that, by the way, because end is a real word. Okay. So when you get to the end, that'll be some condition. Let's say time equals 50 seconds. You want to simulate the entire thing for 50 seconds. But you don't know how big a time step you're going to take. So now you need to do something very tricky. How do you keep track of time? Create a counter, something to track time, progressing, right? So you might start the counter, right? Counter equals 0. Let's say the time starts at 0. And then every time you take a step, increase the counter by, not by 1, h, right? So I'll need some statement in here. Counter plus equals h. Now, do I increase the counter if my simulation failed? No. So this is already kind of telling me where this is going to go, right? So I need to be a little careful. I don't just put this right at the very beginning. This only goes in the success statement. So first thing I need to do is I need to do this. I need to take 2 steps, and I need to take twice as big a step. I need to do RK4 3 times. Okay, let's look at it. You see why it's 3 times? You have 1 value here, right? So this is x1. Everyone starts, or let's call it x0. Everyone starts with x0 as the starting point. And then you have the RK4 value of 2h. And you're comparing that, the RK value 4 of h plus RK value 4 of h. Right? That is not the same as multiplying this thing by 2. So I can be a little bit more specific here, right? I could be like this. Be like x0 plus 2h, x0 plus h, plus x 0 plus h plus h. That's not good notation. We'll see that it's different when we write it. Okay. And those are the ones we're taking the difference of. Is that fair? Okay, so the first thing that happens is we calculate 2 RK4s. RK4, 2, RK4 twice. Right? Then you compare them. You use an if statement. If blah, blah, blah. If success, what do you do? Add to the counter. What else do you do? No, we don't actually, those are something we prescribe at the beginning. Yeah, you're gonna update H. H prime equals H times rho to the 1/4. Anything else? Yeah, this will increase if it's successful. Continue. Right. Before we continue, we want to save the correct version. So we might append to a list, right? X equals X points. Append. Does that make sense? Yes or no? Okay. And then this one is really tricky. This one you may not have recognized. You need to assign your new value is. Because now X naught is wherever you ended up. It's not equals X1 or X2, whatever you, it doesn't matter, they're the same, right? Good. What if you fail? Sure, but what do you do? You're right. That is exactly what we're gonna do here. But what do we do if we fail? You don't increase the counter. You don't stop the counter, you just don't increase it. So you just leave that absent. Do you save the point? No, that would be silly. Just decrease H. So we go here and we say H prime equals H rho to the 1/4. But Krismani, that's the same equation twice. How is it possibly gonna know? It was designed, right? Rho is the ratio of these two things. So when it's smaller than 1, it will decrease it. When it's larger than 1, it will increase it, right? Okay. Does that structure make sense? You see how I did it on the board here and then I wrote it out like this? That's what I want you doing. When I said have paper and pen, this is what I mean. Sketch it out, show the flow, show how arrows feed back to each other. You won't get it right, you know? You'll make mistakes. That's okay. You can kind of see your own logic as opposed to sometimes when you have code, like, fuck, this is a wall of code that I really don't understand, right? Okay. Anything I'm missing in here? We can add more details, but for example, Will talked about the fact that we should never let H increase by a factor 2. That's fine. You could do that. You could also note here, H prime and H, that's going to be complicated. Maybe we don't want to do that. So you can take advantage of the fact that computers are sick animals, and they can go like this, H times equals rho to the 1/4. Sick, right? Cool. What do we think about this? Anyone scared? Good. Everyone should be scared. It's fun. This will allow us to do all of the simulations that we want to do from now on.